Assalamualaikum, good morning. Welcome to lecture 16 for CHM477 Inorganic Chemistry. I'm going to talk about magnetism of coordination compounds explained through crystal field theory. Explaining the magnetic properties of transition metal compounds or coordination compounds using crystal field theory or CFT. My lecture 16 dealt with the splitting of the orbitals of any metal or any transition metal when ligands approach the metal center. When ligands approach the metal, let's do a little bit of a recap. When this is the picture of how how the d orbitals look like when there are no ligands around it. They are degenerate. They are having low energy, quite stable. But when ligands come to the metal center, 6 ligands come to make octahedral field. Splitting will occur as a result of the repulsion of the electrons in the metal with the ligands that are located at the 6 corners of the octahedron. So the EG orbitals, which are the dx squared minus y squared and dz squared, will be destabilized or having higher energy, most destabilized than the T2G. But the reverse is true when you have tetrahedral arrangement, when you have 4 ligands approaching the metal center like this in here. This is your tetrahedral field. Where the ligands will be located in between axes and therefore affecting the dxy, dyz, and dxz, which are the T2G orbitals. They will be affecting or repelling those orbitals more than the EG. So the T2G is at the top, EG is at the bottom, and the magnitude of delta, which is delta tet, is always lower than your delta octahedral, because delta tetrahedral is produced through repulsion of 4 ligands, whereas delta octahedral is produced through repulsion of 6 ligands. And for the square planar geometry, is achieved when you remove the 2 ligands on the z-axis of an octahedral. So originally the octahedral splitting looks like this, but when all the orbitals having z terms become stabilized because the ligands are removed from the z-axis, so the dz squared goes down from this very high position to low position in here because of the direct stabilization of that orbital. Similarly, you have dyz and dxz also stabilized. So this is the splitting, the d orbital splitting, crystal field splitting of a square planar. So that is a recap. So we're going to use that theory, the crystal field theory, to try and explain the properties, the magnetic properties of coordination compounds. A unique property of coordination compounds is the fact that they can either be paramagnetic or diamagnetic. Now, a paramagnetic compound possesses at least 1 unpaired electron. Well, at least 1 unpaired electron, then that compound is called having paramagnetism, whereas a diamagnetic compound will not have any unpaired electrons. All the electrons in diamagnetic compounds will all be paired up. we have we have seen excuse me, we have seen how magnetism was explained through valence bond theory, and this can also be effectively explained through crystal field theory. Now, the magnitude of delta, which is the splitting of the d orbitals, depend on the type of ligands attached to the metal center. When you have strong field ligand, you have delta very big. When you have weak field ligands, such as the halogens, then you have delta quite small. And the size of this delta will determine whether you are going to get high spin or low spin. Now, these are the two new terms that you will be learning today: high spin situation or low spin situation. Yeah, I'm going to explain to you later. Well, shortly. In the magnitude of delta in the splitting of the d orbitals depend on the type of ligands attached to the metal center. Taking manganese 2 metal centers, i.e., manganese 2 has 5 d orbitals, electrons, sorry. Manganese 2 has 5 d electrons. So depending on how big delta is, this is when delta is small, this is when delta is big, there are two ways that we can fill in these orbitals with 5 electrons. So these are the 5 electrons belonging, the 5d electrons belonging to uncoordinated manganese 2 ion. Yeah, uncoordinated means it is not bonded with any ligand. When you have 6 ligands, for example, 6 water molecules approaching this manganese 2 ion, you are going to have splitting happening. Yeah, the splitting will occur where T2G orbitals will be at a lower energy level compared to the EG orbital. Now, I have gone through with you about the electrochemical series where water is a weak field ligand. Yeah, weak field ligand. Where is it? Let me, here it is. Let me take this and then copy it into there so we can have a good discussion on the same page. Yep. Water is a weak field ligand. There you go. This is messing up with me. Yep. Water is considered a weak field ligand, as if you can recall that the donor atom from group 7 are weak field ligands, becoming stronger as we move into group 4. So water is considered a weak field ligand, and a weak field ligand will produce a small delta. Yeah, small splitting. Now, in a situation where you have a weak field ligand and the delta is small, all these 5 electrons can be arranged in this way, where all the orbitals T2G, EG, they will all be singly occupied because it doesn't take much energy to jump from the EG to the T2G. So these 5 electrons will go 1, 2, 3. Okay, have enough energy, jump up, 4 and 5. So this is what we call a high spin complex, where the number of unpaired electrons is at the maximum number. Yeah, the unpaired electrons are maximized. But when you have a strong field ligand, such as cyanide, here, as you can see, cyanide is in the other end of the spectrochemical series of ligands, so it is on the strong field ligand. The splitting of the d orbitals become bigger because the repulsion is stronger. The repulsion produced by a strong field ligand is stronger. So when you have 5 electrons that you have to arrange in this situation, the first electron is single, the second electron is single, the third electron is single. Now the fourth electron has a choice whether it can go up here. If it doesn't have enough energy to jump or to overcome the splitting, it will simply start to pair up, because pairing up will produce less, will need less energy compared to jumping to the next level. So the fourth electron will pair up, the fifth electron will pair up. Now this is the situation when we say that this is a low spin complex. Now please count the number of unpaired electrons in the low spin complex compared to the high spin complex. Now in the low spin complex we only see one unpaired electron, whereas in the high spin complex you have 5 unpaired electrons. Both are paramagnetic because both has at least one unpaired electrons, but the paramagnetism of the high spin complex is stronger compared to the paramagnetism of the low spin complex. Yeah, one unpaired electron versus 5 unpaired electrons. So I'm going to show you a few different scenarios later. So usually a strong field ligand will produce big delta and tendency of producing low spin complex, whereas a weak field ligand will produce small delta with a tendency of producing high spin complex. So that is how we can explain the presence of high spin and low spin according to the crystal field theory. This cannot be easily done when we deal with valence bond theory, because in valence bond theory, if you can recall, there are no information on energy, on the energy level of those orbitals. Yeah, so you can see valence bond theory is way up. Go back to my lecture on valence bond theory if you are not sure what I'm talking about. Now, a weak field ligand such as water produces small delta. When delta is small, the energy required to pair up the electrons is bigger than the energy required for the fourth electron to jump to the higher level, i.e. the energy for pairing is bigger than delta. Therefore, the arrangement of B here is preferred. A high spin complex is produced with 5 unpaired electrons. Now, a strong field ligand, this is actually introduced. This is explaining what I have explained to you. A strong field ligand such as Cn- produces big delta. When delta is big, the energy required to pair up the electrons, or E pairing, is smaller than the energy required for the fourth electron to jump to the EG level, where E pairing, energy for pairing up, is smaller than delta. Therefore, arrangement C is preferred. This arrangement C here. This is the arrangement C. And a low spin complex is produced with 1 unpaired electron. Note that a low spin complex is one with the fewer number of unpaired electrons. That's why we say it's low spin, because each electron will have its own spin. So when there are two, the spin to the top will be cancelled by the spin of the electron going the opposite way, because when you're pairing up electrons, you cannot have both electrons orientation to the top. One has to go to the top, one will be to the bottom. So the spinning of this electron will be cancelled by the spinning of that electron. So you have only the spinning of this single electron noticed. So, but in here there is no cancellation, so you have high spin. Yeah, that is the origin of the word spin. Now let's have a look at octahedral complex. Oh, this is, excuse me. Yeah, let's see. Yep. Let's have a look at octahedral compounds here. Now, octahedral diagram for the D1 through D9 ions in octahedral orbital diagrams, excuse me, orbital diagrams for the octahedral complexes having D1 electron until D9 electrons show that both high spin and low spin are only possible if you have D4, D5, D6, and D7. Otherwise, it's not going to be different. I'm going to explain that to you later. With 3 lower energy T2G available, the D1, D2, and D3 ions always will form high spin complexes because there's no need to pair up. Similarly, the D8 and D9 ions from the high spin complexes will form high spin complexes because T2G set is filled with 6 electrons. The 2 Eg orbitals must have either 2 or 1 unpaired electron. So I'm going to explain that to you later here. Here it is. Let me explain that. Right. Now imagine you have this situation, no electrons first. If you have D1 where there is only 1 electron, you're going to either high spin, either delta is small or delta is big, there will always be 1 unpaired electron. For example, here. Imagine the other 3 are not present. D1, you're going to have to fill in only 1. Similarly with this. So there is no difference between low spin and high spin for D1 complex. For D2 is the same case. You're going to fill in this orbital and that orbital. Similarly, you're going to fill in this orbital and that orbital. No difference between the two. Similarly with the D3, 1, 2, 3 and 1, 2, 3. Now the difference between low spin and high spin will only be observed when you have D4 and D5, D6 and D7 because D4 for low spin has this kind of situation going where you have 4 unpaired electrons, but D4 for high spin, D4 for high spin, the D4 high spin will have 4 unpaired electrons, but D4 low spin will have 2 unpaired electrons because the 4th electron starts to pair up. For D5 for high spin, delta small will have 5 unpaired electrons, but for low spin, delta big will have 1 unpaired electron only. For D6 high spin, you have 4 unpaired electrons, 1, 2, 3, and 4, because the 6th electron will pair up with the first one. But for low spin complex, you are going to have no unpaired electrons. All the 6 will be pairing up before they start to fill in the top one. And D7, for low spin, you have 3 unpaired electrons. And for high spin, you have 1 unpaired electrons. So only for D4, D5, D6, and D7 metals will show difference in paramagnetism or indifference in magnetism for the low spin complex and the high spin complex. When you start having D8, the 8th electron, if D8, will come into here. You have 2 unpaired electrons. For the high spin, for the low spin, the 8th electron will come onto this orbital here. So you are going to have also 2 electrons. So D8 there is also no difference between the high spin complex and the low spin complex. And similarly with D9. D9, for example, is copper 2. The ninth electron will be pairing up with this electron at the top here, leaving you with one unpaired electron. Whereas imagine there are already 8, the ninth electron will pair up and leaving you with one unpaired electron. Yeah? So D1, D2, D3, D8 and D9 will not show any differences between the high spin and low spin situation in terms of magnetism. Only 4 species you will be able to distinguish between high spin and low spin, and those 4 species are D4, D5, D6, and D7 transition metal complexes. Yep. So the explanation is here. Now, you might be wondering what is this new SO? New SO is magnetic moment for spin only. So how is that calculated? So let me explain to you how is that calculated. The number of unpaired electrons, this is messing up. It should be quite big. Oh. The number of unpaired electrons determines the magnetic moment of a particular coordination compound. So if you have a lot of unpaired electrons, the magnetic moment is big because there will be a lot of electrons spinning singly in the same direction. The theoretical values of the magnetic moment, which is called the spin-only magnetic moment, or mu SO, magnetic moment spin-only, can be calculated using the formula below. Spin-only magnetic moment is equal to square root of n into n plus 2, where n is the number of unpaired electrons. So if you want to see what is the magnetic moment of a metal complex having one unpaired electron, you're going to put 1 into 1 plus 2, which is 3. So 1 times 3 is 3. Square root of 3 is 1.73. So when you measure the magnetic susceptibility of a compound and you get a value between around 1.73, then you can safely deduce that that species has one unpaired electron. And one unpaired electron give you the possibility of either D9 or D1. Yeah, we will use that to do some exercises later. If you have 2 unpaired electrons, it's going to be square root of 8. So you have 2.83 Bohr magneton. This is called Bohr magneton, BM. 3 unpaired electrons will give you a magnetic moment of 3.88. 4 give you 4.9, and 5 gives you 5.92 Bohr magneton. And this can be experimentally measured. So you measure the magnetic moment, which is when you measure it experimentally, you say it's mu exp, or mu effective magnetic moment. So effective magnetic moment, when you compare it with spin-only magnetic moment, will tell you how many unpaired electrons you have in that compound. So that is a nice little experiment that you can do in the lab to determine or to try to elucidate the structure of the compound that you produce in the lab. Yeah. So this is the balance called the Gui balance. This is the Gui balance, which is the instrument used to measure magnetic moment of any compound, any transition metal compound. Yeah, we use the Gui Balance. Gui is the name of a person, the name of a scientist. To experimentally, the value of effective magnetic moment mu F can be determined using the Gui Balance. The Gui Balance is invented by Louis George Gui. It is a device to measure magnetic susceptibility. When an accurately weighed mass of a sample is placed in a long cylindrical glass holder, this is the long cylindrical glass holder, when it is tested by suspending it from a weighing balance, partially entering between the poles of a magnet. Here is your magnet down here. You have north pole and south pole of your magnet. So this space has applied magnetic field. So a paramagnetic compound will be pulled into the magnetic field. So when you weigh your compound, it will appear more heavy when you turn on the magnetic field. And heavy by how much, the calculation will tell you how many unpaired electrons. But a diamagnetic compound will be repelled by this applied magnetic field. So this tube will be slightly lifted, will be repelled out from the magnetic field, and the measurement, the weight of that sample will look to be less, will become less than what it should be, and that will tell you that it is a diamagnetic compound. Now, the balance measures the apparent change in the mass of the sample as it is repelled for diamagnetic or attracted for paramagnetic by the region of high magnetic field between the poles. Now, comparing the effective magnetic moment, which is the experimental value, with the spin-only magnetic moment, which is your theoretical value, the number of unpaired electrons in a sample of coordination compound can be determined, hence the spin state or the geometry can be predicted. So let's have a look at this example here. Now, this is one example for identifying complex ion either as high spin or low spin complex. Now, that is a problem that is given to you here. Iron 2 forms an essential complex in hemoglobin. For each of the two octahedral complex ions, FeH2O6 and FeCN6, 2 minus, draw an orbital splitting diagram, predict the number of unpaired electrons, and identify the ion as high spin or low spin. Right, how will you do that? First, you must determine what is the oxidation state of your ion. So from here, you can easily tell this ion 2, because this is Fe, water has 0 charge, so the 2 plus is actually the charge of Fe, so that's ion 2 plus. Similarly, this is also Fe 2 plus because 6Cn minus, the overall is 4 minus, so this must be 2 plus. Yeah. So you determine that your Fe2 plus, you look into your periodic table, you will see that Fe2 plus is argon 3d6. It has electron configuration of argon 3d6. So according to figure 23.22, water produces smaller splitting than Cn minus. The diagrams are shown. So this is the situation where you have water. This is the situation when you have Cn minus, low spin, high spin. So you have 6 electrons to arrange in this way, producing 4 unpaired electrons, and 6 electrons for your cyanide to be arranged in that way, producing a diamagnetic compound with 0 unpaired electrons. So, you have No unpaired electrons, low spin. So the comment here, water is weak fields. It is almost always form high spin complexes. These results are correct, but we cannot confidently predict the spin of the complex without having the actual values of delta and the energy of the pairing. And cyanide ions and carbon monoxide are highly toxic because they can interact with ion cations in protein. Yeah. And you can try and do this follow-up problem. How many electrons, unpaired electrons, do you expect for CN6 3-? Is this high spin or low spin? So you can try that later yourself. So next, we are going to talk about tetrahedral compounds. Tetrahedral compounds. Tetrahedral compounds, as a rule, always they have high spin, unlike octahedral. In octahedral, it is possible for you to get high spin or low spin depending on the type of ligand attached to the metal center. But for tetrahedral compounds, it is always high spin. Why is that? If you can recall, the delta tetrahedral value is always small. Yeah? Can recall this? Delta tetrahedral is small compared to delta octahedral. So there is always enough energy for electrons to jump after singly occupying the EG. The third electron will always have enough energy to jump into the T2G and then fill up the 3 orbitals in the T2G. After all 5 are filled, then they start to pair up. So that is why all tetrahedral compounds have high spins. The magnitude of delta tetrahedral for the splitting of the T2G and the EG orbitals is small and smaller than octahedral. And it is, as I showed you earlier, delta tetrahedral is equal to 4/9 of delta octahedral. These are the reasons, the reasons that I have explained it to you earlier. The d orbitals experience greater repulsion in octahedral arrangement of ligands because they are pointed directly on the axis where the orbitals are, whereas in tetrahedral arrangement, delta tet is smaller because the ligands are further away from the axis, hence the orbitals, producing smaller repulsion. And in octahedral, the repulsion is caused by 6 ligands compared to only 4 ligands in the tetrahedral field, as I explained a lot earlier. Now, there is a reminder here that in a tetrahedral d orbital splitting, the T2G and the EG sets are arranged exactly opposite to that of the octahedral case. And I hope you can remember why that is so. Okay, so that's about tetrahedral. Now we go straight into the square planar compounds. Another one having coordination number of equal to 4. So the crystal field splitting of d orbitals in square planar is as shown here. Yep, shown here, and you already understand that this stabilization of the dz squared, dxz, and dyz is because the ligands sitting on the z-axis are being pulled away in an octahedral to make square planar. And the delta square planar is the separation between the dx squared minus y squared with dxy. So delta is up here. So the number of unpaired electrons for square planar complexes can be determined by arranging the d electrons for the metal center in the split d orbitals. Generally, in the first approximation, d electrons for square planar complexes can be arranged in the manner of low spin complexes because it is always most of the time it is the case that the electrons will not jump to fill up the top orbital. They will fill up these two orbitals, that and there, and then start to pair them up. And then after all of these are paired up, then they go up to the last orbital to be filled in. Yeah. The energy needed to pair the electrons up is lower than it is to jump the delta square planar to start occupying the x squared minus y squared orbitals. So in summary, the following table lists down the number of unpaired electrons that would be expected in a D1 to D9 situation in different coordination geometries and spin state. So this is a summary for coordination number of equal to 6. Obviously, it will be octahedral arrangement. You're going to have either high spin or low spin. How many electrons? How many unpaired electrons? So these are the number of unpaired electrons that you would expect to see if you have octahedral high spin. For D1, it is 1. For D2, it is 2. For D3, it is 3. The same with the low spin. But for D4, D5, D6, and D7, these numbers are different for the high spin and low spin, and they become the same again for D8, D9, and D10. Yep, for the reasons that I have explained earlier in this lecture. For compounds with coordination number of equal to 4, there are two possibilities. Either you get tetrahedral arrangement or square planar arrangement. So depending on the number of electrons, the number of unpaired electrons, when you measure up the magnetic susceptibility of those compounds, you can use the findings to determine whether you have a tetrahedral arrangement or octahedral arrangement. But that can only be used to distinguish the cases of D5, D6, D5, D6, D7, and D8, because these are the cases where you have the number of unpaired electrons for tetrahedral and square planar to be different. If they are D1, D2, D3, and D4, in both cases, you will be having the same number of unpaired electrons, so you're not going to be able to distinguish between tetrahedral and square planar. Similarly, D9 and D10, you will not be able to distinguish between the two. So in summary, you can have a look at these values here, and D1, D2, D3, as well as D9 and D10 configuration or situation are not going to be able to, you're not going to be able to distinguish between the geometries. But in the case of D4, D5, D6, D7, and D8, it is quite possible for you to determine the geometry of your compound based on the magnetism or the number of unpaired electrons found in each species. So magnetic susceptibility measurement is one of a quite useful tool for a coordination chemist to distinguish the possible geometry that will be adopted by the compounds that they make in the lab. Yep. The effective magnetic moment indicating the number of unpaired electrons in coordination number can therefore be used to determine the possible geometry and the spin state, either high spin or low spin. However, this is only possible for 6-coordinate D4 to D7, as I was telling you, and 4-coordinate D5 to D8, as highlighted in the colors given in table above, because the number of unpaired electrons, hence the magnetic moments, will be different for these species here. Right? So there are a few questions that I'm going to be posting after this. And I'm going to stop my lecture number 16 here on magnetism. My lecture 17 will be dealing with colors of coordination compound, and that will be next one. So that's it. Thank you very much for listening. I hope you're learning something, and I hope you understand about magnetism, how you use crystal field theory to make sense of the magnetic properties of the compounds that are being made in the lab or that you find in any quiz or test or exam. Okay, thank you very much. That's it for now. Thank you. Assalamualaikum.